Hello, we have the circuit for part A. We have a diode in series with a 1 kilo ohm resistor and a constant voltage supply from the Digilant. This circuit operates based on the principle that the diode will act as an open circuit until a certain threshold voltage has been reached, which we find is about 0.7, 0.6, and I'll show you that in the graph. But I'll show you working now. The voltage from the input to the ground is about 2.5 volts, which is the input, and across the resistor 1.84 ohms. So you see that voltage drop is about 0.7 across the diode. Here's the IV characteristic curve for the circuit from part A. You can see it takes until threshold voltage, which turns out to be about 0.5 or 0.6, before the diode begins to have linear IV characteristics.
So hi, I'll show you our half-wave rectifier circuit with the diode, the capacitor, and here the 10 kilo ohms resistors. And here we can see, so that's the second part when we remove the capacitor, but it's exactly the same circuit otherwise. And in yellow is V in and in blue V out, the voltage across the resistor, and which is the same from the one across the capacitor. And we see that when the in is positive, then there's a voltage across the resistor, and when V in is negative, there's no more voltage. The voltage is 0 across the capacitor and the resistor, as there's no more electrons going through the diode. So this is the waveform for when we have the capacitor in the circuit, and we can see that the voltage across the resistor, which is the blue one, and it sometimes to increase because charge in time to go up to cross the capacitor, and then it takes a long time to decrease also, as they need some time to go in the other way through the capacitor too. So our waveform when the input voltage is 2 volt peaks to peaks, and we can see that we have this on without the capacitor, sorry. And again we see that when the input voltage is negative, there's no voltage across the resistor, as we saw previously. And it's easier to see the offset, which is around 500 millivolts. If we subtract 528 millivolts to 992 millivolts, it's almost 550 millivolts of difference. So it's a little bit less than the 700 millivolts expected. It might be due to the diode, as we see exactly the same thing in the other wave chain, where it was here again we see that there was only 500 millivolts of offset of difference, so that might be due to the diode.
For part C, we have an active circuit where we have an op amp along with the diode circuit, which is a half-wave rectifier, and you see the output goes through the diode, and it's very similar to before, except now it's an active circuit as opposed to a passive circuit. And you can see the waveforms. This is the output of a higher voltage, and you can see it takes a few microseconds to get up to where it's supposed to be. That again is because the op amp takes time to get to the point where it is, because there's capacitors and things that are time dependent and can't keep up. And the slew rate comes back to a couple labs ago, which we calculated the value, which I'll show you later. So this is with the input signal, the rectifier signal, it just goes along with that. And then when we decrease the amplitude, it still works, which is different than the passive circuit, because in the passive circuit, when the amplitude gets below the threshold voltage, which is about 0.7 theoretically, the rectifier will no longer work correctly. But with the active filter, the active circuit, it does work, and you can see without the input, you still have the slew rate here because it can't get up to speed all at once. And here is the 10 kilohertz one, where the signal is faster, so it looks like it's taking less time. It looks like it's taking longer for the circuit to get up to where it should be, but really that's because it's a quicker signal. So the slew rate will still be the same, just it's zoomed into a much smaller time frequency. And we calculated the slew rate to be 231.99 millivolts per microsecond, which is very similar to the one we calculated a couple labs ago, which was 229 millivolts per microsecond. So we are happy with these results.